We're going to do a couple of experiments that show how large language models work under the hood. So normally when you're interacting with a large language model through a chat app, there's a lot of stuff happening in between you and the large language model. So there's the chat template, which basically formats everything for the large language model so that it understands the situation that it's in and the context of the chat and everything. And then there's the tokenizer, which basically chops the text up into symbols that the large language model can recognize. So we're going to do some experiments to sort of show how these things work. So yeah, let's just show the chat template first. So we're running an open source large language model so we can see how it all works. So when you download a large language model from Hugging Face, if you look in the files and versions, there's always going to be a template. So this template basically just takes a bunch of variables and outputs a formatted chat message, but I've just written a script to just show an example of what that looks like. So yeah, this is an example of what the large language model actually sees. So you'll see these IM start tokens throughout, and basically there are 3 characters in the chat. So you'll always see a system message at the top, and you'll see user messages and assistant messages. So basically, this example is a multi-turn conversation. So the user asked a question, the large language model, which is playing the role of assistant, replied, and then the user asked another question. So when the large language model receives this, it can see that it's playing the role of assistant, and it can see that it needs to write the next response. Now the chat app itself is actually responsible for keeping track of all of this. The large language model itself actually has no memory of the conversation, so the chat app is entirely responsible for keeping a record of the conversation and feeding everything back in on every request. Now the system prompt would normally be a lot bigger than this, so basically the system prompt, so if you can see we're in this example, we're giving it the date and time. If the system prompt didn't include that, then the LLM would literally have no idea what date or time it was. And yeah, we haven't provided any, but if the large language model has access to tools, so that will be things like a tool to search the web or a tool to execute maths or whatever, they'll be specified in the system prompt as well. And if we were using tools, you might see some extra messages in here, which would be the tool messages, the large language model talking to the tool. Anyway, so normally all this is happening automatically, but we're going to do a demo of how an LLM works without the chat template, because that's just an interesting thing to look at. So I've basically written a few scripts here. We're not going to go into how these work, but I'll probably put a link to the scripts. Right, so if we write, so the capital city of France is right in Paris. So we've got a limit of like 20 or 30 tokens or something, which is why we're getting a response of this length. But basically what the LLM is doing, there's no chat template, so it's just operating in completion mode. So it just, whatever it's given, it just continues the sentence. So you could write something else. You could write like once upon a time, and it will just write a story. I keep accidentally resizing this window instead of clicking. Yeah, and you'll get a different story every time it's. So that's basically the native behavior of the large language model, just performing completions. What did I want to show next? Oh yeah, so if you don't provide any input at all, it'll just randomly say a bunch of stuff. So every time we get something different. So it seems to like outputting mathsy databasey stuff. Oops, so this time it's given us some code. So what it's going to give, so it's kind of regurgitating its training data, although none of this will be an exact copy of its training data. And which training data it regurgitates is probably going to depend on the reinforcement learning that was done on it, right? Reinforcement learning is done after the pre-training, and that's going to... But if we provide it a different... So what we're giving it is just a space. It won't let me give nothing for some reason, but if we provide it something different, like if we provide it lm start, yeah, so here it started talking to itself. So this is a reasoning model, so if we give it more length, we let it write, say, 500. This is a reasoning model, so sometimes it will just go into reasoning mode and start talking to itself. Yeah, there we go. So yeah, sometimes it will just like make up a problem and spend ages trying to solve the problem it just made up. It's really funny. Right, what was I going to show next? So, right, yeah. Oh, here, this time we got Chinese. Right, so we're going to talk a bit about tokens because we can do some fun stuff with tokens. So this website is just a sort of demo to show you how tokenizers work. So if we just type some stuff, it shows us how the tokenizer splits up the text. So what that is, a token is basically they're basically symbols that go into the large language model. So if you were to feed it in one letter at a time, it would be very slow, because it would have to do a complete pass through the neural net for every letter. So they chunk everything up into tokens. So in the ideal case, a token is a word, but that's not always the case. Sometimes longer words. So see how banana is one token, but the comma is a separate token. Yeah, anyway, so there's a few interesting things here. So if we just type some nonsense, you can see that it hasn't been able to tokenize that because obviously... So basically the tokens that are used is basically like the vocabulary of the large language model, or the alphabet of the large language model, and that has to be determined before training. So they're going to run an algorithm on their training data, find the most common sequences of characters, and assign a token to each. So like in this case, we got an entire token just for one character because the tokenizer doesn't have a token for this sequence. So this is why when you make a spelling mistake, I remember like GPT-4 would get very confused by spelling mistakes because it gets a completely different token. So if we type banana again and then type it with a spelling mistake, it gets two completely different tokens than it would have normally got. Now to actually see that, I've got another script. So if we tokenize the word banana, so that's what a token actually is, it's just a number. If we tokenize that, yeah, so in this case we've actually got 3 tokens when we spelled it wrong. So yeah, it's there's also a thing people used to do where they would say, they'd ask ChatGPT how many R's are in strawberry. and it would get that wrong. And it's because basically it's not actually receiving individual letters. The LLM just sees through these tokens. Whereas if you do it like this, it does actually see individual tokens. So yeah, a lot of these sort of bugs of, oh, ChatGPT can't count how many R's are in strawberry is actually just due to the tokenizer, which is really just an efficiency optimization. If the tokenizer was always to make one letter be one token, it would just make it a lot slower and require a lot more processing power to train. But yeah, so for fun, to prove that we can actually do one token at a time, I've given an option to my script so that it will force everything into one token. So if we just add -c, well, let's do it without -c first, right? So what was our example from earlier? The capital city of France is so that's what we normally get. Now when we do -c, my script is going to force it to be one token per letter. And see, we get weird glitched output. So the reason it's made a spelling mistake here is because it's just receiving its input in a really unusual format. And it's trying to continue in the same pattern. So it's thinking, right, I've received one token per one letter, so I'm going to continue in the same vein. But it's not how it's normally trained. Normally, I think Paris would normally be in just one. Yeah, the whole of the word Paris is normally one token, but it's received. Well, it will have received. You see, each letter has its own token. I wonder if they're sequential. Like if we do B, C. Yeah, they are. See, A is 64, B is 65. Anyway, so but if we run it again, oh yeah, and then it started talking Chinese. So Qwen is a Chinese model, so it might be that let's ask Gemini to translate that. Right, what spelling errors are in the sentence, right? So, yeah, that's a completely expected thing. So Qwen knows that something's wrong and it's trying to figure it out. As for why it goes to Chinese, I mean, it could be that it's just defaulting back to its native language, since Qwen is a Chinese model. I suspect it might actually also just be that because Chinese has that they have symbols which are basically an entire word in the first place. So it could be that the tokenization pattern we're giving it might actually be closer to Chinese. But if we try it again a couple more times. So yeah, we've got the same misspelling of Paris and a misspelling of Spain. So yeah, it's basically making constant spelling mistakes. We've basically given it, what do they call it, dyslexia. I've seen some different misspellings of Paris. Yeah, see, Pairs. So you can see, like, the large language model seems to know that something's wrong if you see the type of stuff it says. It can tell that there is some sort of funny thing going on with the spelling, but it doesn't quite understand what it is. But anyways, if they were to train it like this, then you could get the LLM to work fine like this. It would be very computationally expensive though, because obviously, I mean, I guess one token is normally like 5 letters or so. Like I think they say, what do they say? A helpful rule of thumb is that one token is generally 4 characters for common English text. Yeah, so if they were to train a large language model to natively operate 1 letter at a time or 1 character at a time, it would work. It would just be really slow. I think you'd need more memory as well because because you'd have 4 times as many tokens, so your context window would technically be 4 times as long. Yeah, anyway, so that was just a bit of fun to sort of show a bit what's under the hood of how these things work.